First things first, who am I? I am Patryk, Wychowaniec. I've got a website. If you're into RAS, neural networks, I know, whatever, you can visit it. There's also links to GitHub and my email if you would have some follow-up questions. I've been working at NXE right here in Wrocław for almost 5 years now, and what we do is travel industry. And, well, basically, this is RAS Wrocław, so RAS Wrocław. And what I'm going to be talking about are, like I said, various optimization stuff I stumbled upon at my work. But today I realized that probably the more catchy title would be how I got our main application from 50 gigabytes down to 13 gigabytes of RAM usage without any hacks, such as actually unloading half of the data. So it works the same way. I just applied some clever tricks to the code, and voila, it uses, well, instead of requiring a whole server, you can run it on your computer right now. But yeah, what does this application actually do? So this is a data format that was invented at NXE. It sort of looks like ini files, but with tables. And what this basically describes is like prices for a single hotel. This is a simplified version because the actual file, which we call contract, but it's not to be related to blockchain contract. This is unfortunate collision of the names. This single contract, which defines a single hotel, contains, well, in this simplified version, just some metadata, such as the ID of the file, whether it's active or not. And in this simplified model, it contains just a table of prices. And prices in this simple model are applied for some day, for some room, like single in this case, for some meal, like room only. Occupancy, which is one adult. And then you have the correct price, so the actual price. In this case, this would be different price for the same date, the same room, but for all-inclusive stay. We'd actually imagine that all-inclusive would be a bit more expensive than just the room, like something like that we'd imagine. The actual files, like I said, are a bit more complicated, a bit more proprietary as well, so I can't actually post them in the entire phone, but they also contain like some metadata like the mappings from the room code to the room name, or some extra metadata properties, discounts, cancellation policies, extra stuff that you actually either see directly when you go through like booking.com or whatever, or you don't see it just like for tax purposes, whatever. And yes, in reality, the files are obviously also much larger. So we can imagine that we've got prices for multiple days, multiple rooms, multiple occupancies, meals, whatever. And what our applications, plural, do is that they allow you to operate on this type of files and then query for it. So the application that I was optimizing for the purposes of this talk is called, well, Accelerate. This I can say because it's public, but no, not necessarily the rest of them. And what Accelerate does is that you feed it this type of data. And then you can issue a query such as, 2 adults looking for a hotel in Berlin, find me the cheapest price. And in this case, it's a single file that describes single hotel, even in New York City, for the purposes of this example. But we would imagine that this program would go through all of the files, all of the hotels it knows about, and find the cheapest price, ideally under 1 second. But, well, if you go over a couple of seconds, it's basically meaningless, so ideally under 1 second. In practice, in about a couple milliseconds. So I'll just rephrase the question. So the question was if we don't have any SQL database. We do have. We actually use SQL database on like as a storage, for a sort of blob storage for those contracts. And the reason for that is that this file also is used as an input from other people to us. So if we like integrate with different suppliers, we can ask them to say that this is our data format, please provide files to us in this way. And we also have a JSON format of this one, but for this is a single rule in here that you basically understood by now, that this is date, room, meal, occupancy, and price. In JSON, this spans for about 20 lines, because you have all of those different nested objects, and it becomes infeasible to actually, well, either write tests in it or to, well, for humans to debug it. So the file is, well, like I said, we have JSON in this format, but this format is more human debuggable, I would say. Yes, we are, well, I said yes, but no, we are not, we are not using any graph databases. It would be cool. We also don't use neural networks yet, if that was maybe some of the follow-up question, because it's frequently also associated with hotels and pricing and whatnot. So we don't have any graph database yet. And at least for the purposes of, actually querying for the price, graph database wouldn't come handy that much, but like, yeah, for like finding similar hotels in this area, then yeah, could come handy. Yeah, so the first optimization is indexing. So in reality, to bring this format a bit closer to how it actually looks like, the prices are not specified for a single day, but for a range of dates. And then, if you wanted to model it in Rust, you would do, naively, you could do something like that. So you have an abstract that defines a single price. It's for some dates, some rooms. Well, it says room in here, but it can be actually a comma separated, and it will come, it's important, and it will come back later. So we have dates, rooms, meals, occupancy, and the price. Obviously, in before, price wouldn't be actually the float. It's not actually the float in our implementation, but for the purposes of the demo, I would say it's float. And then you have some query. So for some date, for some room, meal, and occupancy, you would return the price. So basically, the whole application boils down to this single function, which takes some prices, some query, and returns, some prices, some query, and returns you some price if it matches, or none if there's none. And the first issue is that if we were inside this FN query actually iterate through all of the prices and just find the first matching item, then this would be too slow for practical purposes, because we are talking about 10 gigabytes worth of prices, so those single lines of items. And if I were to do that for all of the requests, and there are tens of millions every day, it would be, you just gotta trust me, it wouldn't work. Computers are not that fast, unfortunately. So the first thing you can do, the first one that comes to mind, except for uploading the prices to SQL database, possibly, the first thing that can come to mind is to index those prices, for instance, by date. Because if we have a query for a single day, and we've got prices for the whole year, then if we narrow down the prices to just, well, reduce the dimension by one to just the dates and then the prices, then obviously the code in here gets simplified, because first we don't iterate through all of the prices, just the one that matches this day, so this makes it faster. And this is more or less how the implementation used to look like. And the first problem with this approach is that if we take a look at the input data, the prices in here can be specified for a range of dates. So if we later index them by just a single date, then if a price spans for 7 days, it has to be cloned 7 times in order to, well, to be placed inside these different vectors for each of those dates. And this wouldn't fit inside the RAM. And if it doesn't fit inside the RAM, we will not be able to serve it fast enough to later, if we were to read it cold from the hard drive. So the issue with this is that it would take too much RAM. So what you can try to do is, instead of storing the owned prices, you can store references to them. So this way you store prices in one place of the memory. And even if the price spans for a whole year, you would then, instead of cloning the price 365 times, you would store 365 references, which is feasible. Might not be the optimal thing to do, but feasible. But the problem with this approach, with lifetimes, sorting them this way, is that if we were to actually model this sort of struct engine that contains all of the data, you would quickly stumble upon a problem known as self-referential struct. So we have those prices, which are owned, then we have those indices, which contain borrowed data. And the problem is that we cannot actually name the lifetime in here, because this is sort of, if we were to try to name it, this is sort of like self-prices. So we have one field that refers to data from another field. This is known as self-referential. And they are very problematic in Rust to the point that you actually cannot do this within the safe Rust without some extra proc macro crates that do the unsafe tricks underneath. Because the compiler is currently not able to reason about those self-references. If you reference it from somewhere, you have to reference it from the elsewhere. Which also doesn't work in this case because we don't want to reference them from elsewhere. They are like, well, a field above. And naturally, what you would try to do next is, well, possibly get frustrated, go to Reddit, Stack Overflow, and then you would read that instead of using references, you should just store the indices. So in this place, where we previously tried to keep pointer or reference to the price, you would store the index into the vector of prices. This is all right. This is doable. This is how it was actually, again, more or less, with a pinch of salt, more or less implemented. And then the code for querying is not too complicated. Instead of going to the prices directly, we go through indices, find the prices that match the date we've got at hand, and then map them back to the prices, well, map those indices to actual price objects. And this was fine and dandy. This was working this way for a couple of years, actually. But this poses a very serious RAM issue. That's not really obvious at first sight, but the actual code uses a bit more complex index. So if we were to, you can imagine that the actual code does something like, instead of indexing just by date, it indexes by the room code, meal code, and date. So the more fields you've got, the more we can narrow it down. And then, well, that's not new line, supposed like that, maybe a bit more readable this way. We map from this key to the list of prices that match this key. And if you use usize for the purposes of that, then you will waste a lot of memory. And actually the optimization I'm talking about allowed to reduce the RAM size from 50 gigabytes to 40. Just the thing I'm talking about right now. So I noticed that if you use usize, then on 64-bit, so like typical machine you have right now, then this corresponds to 8 bytes, like U64. But by the time you already have this sort of complex key, in practice, you will not be able to exhaust all of these numbers you are being given by this huge, huge type. In practice, I noticed that frequently, when we get to this point of indexing by this tuple, we actually get about from, let's say, 0, well, not 0, from 1 to, let's say, 100 prices. So if we were to use so if we use only in practice the last byte of this 8 bytes, then 87.5% of the RAM stays being just zeros if you use vector of u sizes. Because, well, we don't use that high numbers, so it's wasted space. On the other hand, we wouldn't want to just use vector of u8s, so the smallest type possible where we could use it. We don't want to do that because in some cases we can have more prices than that, so we can get 300 prices, let's say, and we want to be able to still handle it correctly without panicking. And if you'd use U8, we would have to panic it because we wouldn't be able to represent those indexed prices. So what the actual code does, and for that I should have the code in here. What the actual code does, what I implemented, was sort of dynamically growing vector, where it starts as a vector of U8s, but if you push to it a number that's greater than 255, it upgrades itself to vector of U16s. And then in the rare case that you need to store numbers greater than 65,000, 64, whatever, greater, it upgrades itself to vector of U32s. It doesn't require any unsafe code or anything, and, well, basically I can show you the whole code for that. So we've got this, first of all, the key ingredients. So this enum, which represents the vector, the combinations of it. And then we've got a couple of public methods, such as push, which you would normally have on a vector as well. And what this push does is that if it detects that the price can be fit within U8, well, not the price, the index of the price can be fit within 8 bytes, then it's all right, it stays being U8. But if the price is larger, then it upgrades itself to this larger vector. simply by copying all of it. Can I maybe do it a bit more readable? But what it does basically is that it creates a new vector, simply copy-pasting what it has inside of it, and casting the numbers to this higher value, and recollecting into larger vector, which is as simple as it takes. This is a bit wasteful in the sense that if you were to continuously rebuild, well, push lower indices, then to push larger number and would only have to copy this vector all the time. But in practice, this only happens once every while when we have to actually rebuild those in database indices. So this is, well, all right-ish. And like I said, this allowed me to shed 10 gigabytes of the RAM that was used basically on storing zeros in the database because we had vector of U sizes. And this is not even the final form, because today I realized that you can actually do even better, because you can just use a bitmap in the sense that we store all of those prices, but we don't care about their order. So if you want to store prices with indices up to 255, we don't actually need a vector of U8. We just need a bitmap with 256 bits inside of it. So that's 4 times U32. Because we don't care about the order of the insertion, just as long as we know that, yes, price number 32 was inside of it, yes, price 33 was inside of it, and bitset will allow us to do that. But maybe I'll try to work it over the weekend. So yes, that's minus gigabytes. And before I move forward, any questions for this part? Mm-hmm. Mm-hmm.
But the size of the index is basically determined by the biggest index, so technically by how many elements are in your biggest map, in the index, the base map.
Mm-hmm. Mm-hmm.
So what I'm wondering, is there any correlation that the indices actually close to each other in the vector? If so, why not to use the U size as the first index, so to use it on the guide, and then vector of offset only. And offset then would be probably between U8 always.
All right, so to rephrase, the question was about designing the structure differently around the concept of offsetting it. So yes, if this was possible, so if it was the case that we don't have high indices, we just get indices that are shifted by some value, then we could actually use U size as just the shift value and then store prices in U8 and then add this shift while retrieving those. But in practice, the indices here can be treated as random for our purposes, monotonically increasing but random. And there actually exist other smart solutions to this problem. I stumbled today upon Elias Funnel encoding, which I won't be actually delving because it's like a huge article, but basically what it says is that if you have a list of sorted list of numbers, you can encode it in such a way that if you have like 132-bit numbers, normally you would need 100 times 32-bit memory to store it, but if you know that those prices are sorted, then you can use less bits to store them by using the fact that they're consecutively, they're monotonic. And I would also like to experiment with it, but that's for a different part. I'll just mention that this is called Elias Funnel encoding because it took me a few hours to discover it today. So might come handy for somebody else. All right? Yeah? Yes, we also do, acid yes, but again, the answer is no. We do benchmarks, and the CPU performance remained more or less the same, because it's also important. So yes, this is always a trade-off between memory and CPU. In this case, it was win-win because the memory got reduced by 10 gigabytes, but the CPU performance remained more or less the same. Actually, it even got the re-indexing process that builds those indices got 10 seconds faster because it uses less memory now, so it has less to allocate. Yeah, and probably more things fit in cache, stuff like that, yes. Yep. All right, so to answer the question about the databases, why not use SQL, I think I will leave it to the end because maybe some of the stuff that I'll go through will give some idea why using SQL might be a bit hard in here when I bring more complex examples of how the prices are actually modeled. And yes, that's a valid question. I'll just going to, is it all right? Cool. Yes, so the different kind of optimization, it's called the coalescing. Basically, if we simplify the model a bit more for the purposes of the example, we've got just room, meal, and price. Like I said, these rooms and meals can be comma separated. So if we have those 4 rules and they happen to have the same price, then actually this is a very wasteful representation of the prices because we might as well just define them this way, so like compressed, or ideally compressed to this one rule. And this is better not only for the storage, but also important, but also for how those rules are represented inside the RAM, because it's less items to process in a way. And in this case, this was a very simple example because we could even see that they should somehow compress. In a bit more convoluted example, it's not so easy to spot how we could compress those. And the model that I think represents this correctly, but I am not sure, is that if we imagine, for this example at least, that we have some 2D matrix, then what we want to do, well, if we had those first example with just for prices, what we want to do is put those prices inside this matrix, and then we want to create, and to cover those points with rectangles, but use as least rectangles as possible. So in this case, we started with four prices. So the first example, we put them in here. And if you were to grab all of those points inside a single rectangle, yes, rectangle that happens to be square in this case, we would produce this single case with comma-separated rules from before. So this one, like this. This is like this outline of this. And similarly, if we follow the same sort of algorithm for this more convoluted example, we get this shape. And this is more funny because it gives us a couple of opportunities how to draw rectangles, well, at least rectangles, to follow, to encompass all of the points. For instance, we can do it like that. So we have one rectangle that spans from apartment room and covers all-inclusive and room-only meals. Then for the double room, we've got second rectangle that follows all 3 meals. And for single, we have third rectangle. And this would correspond to this inside the notation. But this is actually not the optimal solution for this, well, data input. Because we can as well do it a bit differently. We can do one rectangle that's 2 by 3 that spans across those 2 meals and 3 rooms. And we can just create one rectangle out of the one point that was left at the end. And this gives us this optimized output. And have I repeated myself? No, this is a bit different. And this is important both for the RAM and for the storage. In practice, for this, it allows us to compress what was initially a 50 megabyte file that contained prices for just a single hotel down to, I think, 5 or 8 megabytes, just this compression itself. But yeah, I know, I said that we do it like that. We see some rectangle. Obviously, computer cannot see rectangles, cannot see points as well. So what I think is no, I cannot say it's the correct, because I would in a moment say that it's certainly not correct, but what I think, what my best hunch toward what the actual problem here is that if we convert those points into rectilinear polygon, so polygon where we have only 90 degrees or 180 degree differences between points, then I think this problem reduces to what's known as the polygon covering problem or polygon partitioning. And basically it's well, heated discussion is said a bit too much, but there is this concept of when you have a polygon and you want to decompose it into the least number of rectangles, then this is known as polygon partition. And there exist some algorithms, but they are either NP-hard or, at least for the purposes of rectangles, I think it's O(n to the 4th, which is impractical because I just said that the initial file has 50 megabytes, so probably n to the 4th algorithm is not going to make it. But I think that's my best hunch for now, and in a moment you will maybe see why not. And yes, for that I can also show a bit of Rust code we've got. Well, this basically is some example I wrote down that does similar thing to the example I just shown. So this is the initial data, this is the compressed data. And what the algorithm does is that, well, maybe I can do the actual example by hand first and then show some code. But if we were to go to this example, what the code does is, first of all, it separates elements into separate buckets that certainly cannot be merged together. Like if this was a different price, then those two couldn't be merged into like AI RO. Because it would change the outcome, because initially AI costed 100, let's say euro, and after this operation suddenly it's 150, so that's wrong. So the algorithm starts by separating items into buckets that certainly cannot be merged. And then for each bucket, the algorithm just starts with the first item, checks if it merges to the second one. If not, checks first to the third, to the first to the fourth, and then after some couple of examples, it says that, oh, probably not worth it, let's move on. And it basically does this O(n) to the square for each of those buckets with some cutoff time. So we don't actually, if this bucket had 1,000 prices, we wouldn't actually be checking all of them with all of them, but like first with up to, let's say, 100, then the second up to 100 first, and so on with some like limiter. The algorithm is relatively straightforward. I mean, it is implemented in a bit optimized way, so like not necessarily as straightforward as I just described a simple algorithm would be, but not too complicated. So there's basically a trait that you would implement in this case for this price struct. You separate prices to some buckets, and then basically you have to provide function that allows you to say whether if you merge current item with some other item, whether it succeeded and the price got extended or not. And the actual algorithm below boils down to, well, first building the buckets, which uses just a hash map, and then walking from the first item, checking the following items, and finally moving on to the second item, third, fourth, and so on. And this was an optimization that allowed us to share, in this case, storage, like I said, from about 50 megabytes per file to about 5, which is a nice win because we were running out of storage on that server, and it took like about 3 days to discover, test, and make sure it's working. So quite a nice, I think, time trade-off. All right, before I move on to the last segment of this part, which is why I don't think this is the proper solution, do you have any questions for this? Yeah? Mm-hmm. Mm-hmm. Yes. Fair question. Yes, to the power of 4, it would be very, very bad. Even n squared on all of the prices, when you had millions of them, would be bad. That's why we first separate them into those buckets, which are about 1,000 items. And to answer the question directly, the algorithm on this huge file takes about 10 milliseconds. Yes, and there's no multi-core, threading, anything in there. It's just this while loop that goes through the items. And I think the only non-obvious thing that I had to use is a function called getManyMut, because we modified the items in place, I couldn't keep mutable references to them. So similarly as with the engine struct from before, we use indices. And then the issue with the function is that we had to get having those two indices for the items we wanted to check. We wanted to get 2 mutable references to these items. To the left one to pull data out of it, and to the left one to push data into it. That was like this, for instance, to move room codes between the items. And if you use getMany, like if you would something like that, like head, get mut head idx, and then the same for tail, then the compile, and then you do some operation like I don't know, head, merge, tail, whatever, or whatever that takes mutable on both sides. And the problem with that is that the compiler isn't able to reason about that those indices are disjoint or different. So it would say to you that you cannot actually call second getMute because you already called getMute in this place and you keep the head alive after, well, at this point. So this would be two mutable references to the same point in time, to the same value. And there's a function in nightly Rust called getManyMute that allows you to do that because it validates that the references you give it are not references, that indices you give to it are two different indices, or three different, four different, n different indices. If so, it just returns you OK and mutable references to both of them. So this can come handy in cases like this when you have multiple indices and have to get mutable references for them. Right? Any question more? Cool. So now a quick segue into why I don't think this is the actual proper solution to that. So this polygon decomposition, while I think it's not the actual solution, is because if we take a look at some example from before, like this one, and this should be actually closed, no, like this one, yes. So this is a valid input file. In this case, we say that the all-inclusive and room-only for the apartment costs the same, which obviously wouldn't be true, but good enough for now. And if we were to do this matrix from before, then this matrix would say that we've got first rectangle that goes in here, magically spans in the third dimension into here, and then we've got this double room defined like that. So without that, because that's confusing. So that's like this file in this matrix representation. And if you move it to third dimension, you can sort of imagine that this APP in SGL, they're sort of like cylinder that touches sides, and then this double room is like going up, I guess. But I don't know, it's probably not worth discussing too much even, but I figured out that this could boil down, this whole problem of how to merge the prices effectively, this could boil down to polygon covering problem. It sort of matches my intuition, but like with this example, it proves that it's not exactly the polygon decomposition. So if you later happen to have Eureka moment, feel free to write to me, because it's my night that that this should be a solved problem, and the best I've got is some naive, greedy algorithm that tries to match everything and, well, it's fast, but maybe there are better solutions. Right? Different kind of problem. Prices are more complicated than just days and rooms and meals. For instance, prices can be specified for some stay length. Like in this case, we say that the price is €100 for single room only if you stay for one night. If you stay for 2 nights or 3 nights, the price is different. And the price is also different for the meal combination or different room. In practice, this rule is defined as sort of an enum with multiple different options. So the rule can be, well, nope, so no rule whatsoever. This can be this: you have to stay at least or exactly n days. You have to check in on this day. You have to check out on this day. For some occupancy, like weekdays, like say on Mondays the prices are lower, but on only if you departure on Sunday. Hoteliers can be very imaginative. And you can also combine the rules with like ors and ands and nots, and this is actually used in different places. So like I said, this is not as simple as an actual table from some combination to some value. This is takes actual interpreting to produce the price. And the problem with those rules defined like that is that this takes 4, 5, 6. This takes 7 bytes in the input file, but the actual enum rule we've got takes 80 bytes in the memory to store. That's 80. That's some serious some serious bytes in there. So after this is parsed inside the memory, this whole rule object takes as much space as these two merged lines would, just to store this stay one information, which is a bit counterintuitive because the stay one information takes less information when it's in the textual form, but more in the memory. But when you have multiple rules, they contain some nested objects. This can get pretty big. And you might also notice that the rules are not that unique. So sometimes they repeat, and they actually frequently repeat. Like in this case, we, in a way, have 9 rules, but in another way, we have just 3 rules, because we have just stay 1 rule, stay 2, and stay 3. But at the same time, if we were to pass them just like that, this would take not 3 times 80 bytes, but 9 times 80 bytes, because we don't reduplicate them in any way. And the first thing you might try to do is to use arc, or just another reference counted type, which would allow you to pass the rule just once, and then clone it. And then this clone, because it's wrapped in a reference counter smart pointer, this doesn't actually cause the whole rule to get cloned. It clones just some object that tracks how many instances of this rule are being tracked. So if I have one rule that takes, let's say, 1 kilobyte in the memory, because it's so huge, if I wrapped it in arc and clone it, then this clone doesn't take second 1024 bytes. It takes, let's say, 16 bytes for the pointer and for some counter to say how many clones are still alive. And this would be a good solution, but we can do even better. Because the problem with arc is that it's actually 2 usizes. So it's 1 usize for the pointer to the data, and the second usize for the counter of how many clones do we already have. And the second counter is incremented when you clone, and is decremented when you drop. And when it reaches 0, the actual underlying object gets destroyed. And the problem with that is that it's also a bit wasteful, well, pretty much wasteful. We can do it a bit manually. By doing it a bit manually, we can drop this by half, because we could imagine that we could just store a vector of the rules. Or, bit reset, hash set, but for the purposes of this example, vector is good enough. When we would try to put something in this vector, we would first check if the item is there. If so, we would return index to it. And this would allow us, so following this example, we would put in here just 3 stays. And the duplicated stays would just have the same rule ID, IDX, and it would be copy-pasted. Similarly, you could say that in practice, we will not reach 64 bits. We will not exhaust this addressing space, because if we had more than, what would it be, more than 1 million rules, we are already screwed up. So in practice, U32 could be enough, or even less. But we can do much better by noticing how the actual data looks like. So while we do allow some complex combinations, such as if you arrive on Monday, you leave on Sunday, and the stays for 2 days, you pay €100. Frequently, the rules are very simple. So frequently, it's just like 90% of the prices are just stay for n days, or well, basically just stay for n days. And the other combinations are used, but infrequently. So what we can do is create one type of price that's optimized, where we assume that with the rule we had was stay, and just unparse it. We also can notice that stays usually don't span more than a couple of days, so 255 days should be enough for everybody to stay in a hotel. And also, even though the price was initially F32, we can actually notice that we can store it in U16 as sort of U16? No, to U32. If you store it as a part of the real component and the fractional component. So if we had prices like 1, 2, 3, 2, 2, 32, then we would store it as, simplifying a bit, 1, 2, 3, 4 times 32. But now that I mention it, it would be not worth it to do it for float, because this would be the same. So let's just say that we do it because the stay is lower this way. And this way we keep the original code for the whole rule in here, or use this arc or usize. And use this optimized layout for rules that are specific. So in this case, this optimized price is one that has dates, uses 1 room, 1 specific meal, has the stay rule, and has, well, some price. And this way you can store the optimized prices in separate vector than the regular prices. And because the ordering of the prices doesn't matter, because in principle, every query should match at most 1 price. There's no order in between them, such as if you have overlapping prices, the last one wins, nothing like that. At most 1 price for a query. That's why you can store them basically in this optimized format. And and this shed of another 5 gigabytes, I think. And it's not even too complicated of an optimization, but it does depend on the input data. So because we analyzed the input data, we could see that there are some frequent patterns, and we could optimize for them. It was easy, quick win. Yeah. So this is something that we would not be allowed because this state overlaps with RILE on Monday. Right? Any questions for this optimization? Yeah, Patryk?
Yeah, I'm wondering about the optimization procedure. First of all, I think you keep the rule in an arc, right? And or some kind of. Now, I assume that the reason why you need 8 bits for your rule is that there is one binary vector. Why not just make the trace rule and store everything as a dynamic trace and dynamic impact, and always have like small bytes there, unless you actually have big type. Did you try that maybe?
Yes. So the first reason, to rephrase the question is why we don't use trait rule instead of huge enum. So we would imagine we would have trait rule with some function like, I don't know, is matching some query, and then we would do struct stay and implement rule for this. The reason for not doing that is that if you have box, then rule, then this is actually, the box itself is 2 times usize, and then you have to actually include the size of the underlying struct. So in this case, this would be probably 4 bytes because it would be padded to U8, but let's say this would be 1 byte. But you still have to pay for the box for how large it is. So
You still have to cancel that.
yes, well, yes and no. So to answer a bit directly, we don't use trait for this because it's difficult to parse it back. No, to parse it, not to parse it back, because currently the code has this enum rule, and then we have from str for a rule, and then all of the dispatching, all of the checking if the string contains, I don't know, stay or whatever, it is within this implementation. But if we had a box of the rule, it would be a bit difficult or more awkward to actually code it because you would have not closed set of the possibilities, but an open set of possible every rule. It would be more difficult to track it. But what could be done is that we could find the biggest structure. So if we would imagine that this takes, I don't know, 75 bytes, we could box that one. This would take the size down to 16, and this could possibly reduce the size of the whole struct to just 40, because there are some types within this enum that must occupy the space, so intuitively it should be possible to box them and thus reduce the size, but I don't know, we have not tried it yet. Just not tried it. Right, before we move on to the last section, any question for this one more? Yes, so this is just a simpler example when I didn't want to model the actual architecture, but internally the code, instead of having like, this was this hash map from before, this is not designed like that. It's actually like B-tree map from room code to, let's say, room indices. Then within this room indices, there's some metadata and pointer, and then second map to mil codes and stuff like that. So this is a bit more structured in the actual implementation, but this would be too long for the example. Yeah. Right? Compacting strings, or compact strings in this case. So we get this model, back again, simplified a bit because we don't need rules for this example. And the problem is that a single string takes at least 24 bytes, and then the size of the actual data. That's because a string is essentially a wrapper for the length, the capacity. So how much, so if you have vector of, to explain some difference, length is how much you've actually written into vector or pushed, and capacity is how much more you can push until you have to grow it. So you can have vector of capacity 100 by length, but length is 5, which means that it has 5 elements, but you can push 95 to it without having it to reallocate. And then you have the actual pointer to the actual data. And those are all usize, and this is also usize internally. So this is 888 plus the size of the actual data. So whatever this points into. And what this boils down to is that if we have those 3 characters in the input file, then if we parse them, they would actually be parsed into 27 bytes worth of memory, because we would allocate the string with length, capacity, and data pointer, and then we would allocate the 3 actual bytes that we mean. So this is very, very wasteful because we've got very, very lots of rules. And, oh, it collapsed. And it was rather wasteful. Amazingly, this optimization only allowed to shed 1 gigabyte from the data, but I also applied it at the end. So by then I had like, let's say 20 gigabytes, reduced the data set from 50 to 20, and then doing this optimization that I will talk about right now allowed us to shed 1 gigabyte more. So nice win because it was easy to implement, but not dramatic. So how can we do better? Well, we can try to use references. In this case, the reference would be, well, we would still have to allocate the string somewhere, but ideally we would allocate 1 string and then just point to it. But this is the problem we've already faced in the previous sections, which is that if we try to do that, we actually stumble upon this lifetime issue with self-referential vectors, which is difficult and not possible to do in safe Rust. So that's a pity. We can do usizes, which would work. It would be sort of better because, well, it would be easy to implement. We would try to allocate 1 index. Out of the more, well, easy to apply optimizations is that we can use this funny box str type. And the difference is that if string is length plus usize plus data pointer, so it's 24 bytes plus the actual data, then box of str is just the length and the data pointer plus the actual data, so it's like 8 bytes less. And the trade-off here is that you can modify the string by just like pushing more characters into it. So we have like string builder. Each time you have a string, you can modify it. But when you construct a box of string, box of str, not box of string, it's sort of read-only. I mean, you can overwrite it with different box, or you can, there are like 2 or 3 functions you can execute on it that modify the string, but for all practical purposes, box str is frozen in time. This way, it doesn't have to store the capacity because it doesn't need capacity because it's frozen in time. You cannot push more data to it, so why bother? But it still is like, you can still feel that we would pass what's 3 characters in the input data into 90 bytes in the memory, so that's still a bit wasteful. And there are a few crates that implement a type called compact string, compact str, and just like, I don't know, like 10 of them. They implement it a bit differently and name it a bit differently. But it boils down to the fact that we can create our own string where we could encode some of the data within it. So if we imagine that, for instance, we can assume that if we define it like that, we can say that if the length is 0, no, bad example. If the length is U64 max, then instead of allocating data, we can store 8 characters in here because U64 is just 8 times U8. So we can have this special code that if you try to allocate string, and the string is less or equal to 8 bytes, so 8 characters, instead of actually allocating the string, we would say that its length is U64 max. It would be this special canary value for us. And then the code knows that if the length is U64 max, then actually this is not data pointer, then actually this is just the actual data in line. And this would allow us to shed what's box str in here to just just 16 bytes for strings that take 8 characters or less. This is still not the best not the best trade-off, because we went from 27 to 16, so this is not that much, maybe. But it's there are already crates for that. It's easy to implement them in your code. Not even implement, just pull into your code. You basically replace all usages of, like, I don't know, to do x to string or maybe x into. It's just, instead of specifying that you want to put that into a string, you just say that you want to do that this special compact string or whatever the particular type is called. And the libraries make it rather easy to use. So this was basically took an hour to actually apply in the code, and it allowed to shed 1 gigabyte more. So while it was not the greatest memory shed in here, it was still worthwhile because it was easy. The libraries are also proven. I guess, any questions for this part? Yeah?
I'm wondering if you try the same optimization for all those vectors, because I see from the vector field, and literally like switching that to
Yeah.
save you capacity.
Yeah, we also have.
Maybe even for vectors.
We also use box of slices. So instead of vec, I don't know, string, the actual code might have something like box str. And this type looks very funny, but the principle is the same. So the vector takes length, capacity, and actual data, while if you use box of slice, you have just the length and the data. You cannot modify it. And you might ask how to construct it. Well, this are called, on the vector, there's a method called, I think, into slice or into box slice, probably. So basically, at one point you parse, then you decide I've got all of the data at hand. You call vec into box slice, and you've got this type that weighs 8 bytes less, which is not much, but it's on one hand it's not much. On the other hand, it's very much if you've got millions of the same similar items. So yes, this is. Yeah.
The optimization I'm thinking in my head, what if we just said the maximum movement is 8 characters, or 10 characters? That saves a ton of things.
So to repeat it, the question was about why don't we enforce a company-wide policy mandate that room codes or meal codes must be, let's say, 8 characters or less, so that we don't have to even use compact string. We would just store them as, I don't know, U8 or something like that, which would definitely shed off those extra 8 bytes. And the reason we don't do that is that the system was supposed to be extensible. So when we pull data from external companies or push data to some different companies, they do have funny rules like that. Some in particular have limit of 3 characters for room codes. And that's because some guy in his million light years ago wrote some code in COBOL and said, well, who would need more than 3 codes, 3 characters, and we have to work around them. So I guess the reason, I can only sort of imagine, because I was not the one doing this decision, and I'm also not the one that would revert it, but I would imagine that the reason was that we wanted to be extensive, knowing that the rest of the world has those mandates. So seemingly random policies. Sorry? Oh yeah. The question was about using small vec. I also benchmarked small vec. It did not bring measurable memory differences, but it made the code a bit slower. So this was like worst of cases, unfortunately. No, we do. Yes, I know the optimization. We have not tried to do that, mostly because the code with those optimization applied is actually good enough for the time being. So I have not tried to apply any more fancy optimizations. but I know some are possible because even if you take this 5 megabyte file that's already compressed and whatnot, if you still zip it, you still get like 1 megabyte output. So there is some high entropy data in there that should be able to be coded better. But it's like good enough for the time being. So all right, then let me just go back to the first page in case you wanted to find me later. So Patryk, pwy.io. You will find also contact there. And well, as a presenter, thank you for listening to me, and also thank you for being at Wrocław.